So without any further ado, I would like to invite Zivid for the first talk, which is understanding the main source of error in vision-guided robotics. The stage is yours.
All right, thank you. Can everyone hear me okay? Well, good. Yeah, welcome, or thanks for having me. I guess I'll warm it up for these guys. The big hitters are coming later. I'm Øyvind, and I'm a VP of Products in Zivid, and I'll talk a little bit about the concept of getting a robot to accurately do what it wants to do. I put up this picture of this needle because a lot of you guys are going to build robotic systems where you really try to thread the needle, make it really accurate, and perform the tasks you will reliably. And there's this topic, we call it trueness, which is very related to basically how you can rely on the 3D point cloud to accurately guide your robot in the real world. So we'll talk a little bit about that, and then I'll show you briefly basically the concepts of how we qualify products here in Zivid, so you get an understanding for what that means in terms of trueness, which is very equivalent with basically point cloud calibration. So here we have a point cloud of various metal pieces. And when you get your first 3D camera to assess for your application, you typically assess the camera's sort of first order reconstruction characteristics. So you take the point clouds and you look for, so for example, are the items of interest reconstructed in 3D? For example, shiny objects, as we see here, can be very specular and require a large dynamic range to be seen. Is the point cloud dense and complete enough? It's like, are there holes present? Is the density low? Are there missing features? And is it free from false points? For example, what happens if you have interreflections or highlights or maybe a contrast region? Does the point cloud start to distort and be deformed and whatnot? Does it preserve small shapes and details? Can a point cloud be created in sufficient time? And all of these different assessments, they weigh in differently for every separate application. Now, let's assume that we found a 3D camera for our application which fits the bill for all of this stuff. So we plug it in and we capture the point cloud. So we do a digital, or basically an analog to digital conversion of the real world into a point cloud. We detect some objects with our vision engine, and we pick a couple of candidates. And then we estimate the pose of some of those candidates. We check for robot collision so that we can enter and grasp it freely. And then we instruct the robot to go in and grab it and place the object precisely at its destination. And this is where the crux really is. It's when you go back into the world to really basically translate from the digital domain back into the analog domain. And this is where basically this is where we basically hope that everything works fine. However, what's quite often happening is that the point cloud does not really correlate with the real world. So the good detection that we had is really only the first hindrance. So when we're interacting with objects in the real world, we really need that coordinate system of the point cloud to match that of the robot and the objects that we wish to manipulate. And this is what trueness is all about. It's about measuring and interacting with objects. So trueness is a term that basically describes large-scale errors and distortions and deformations. And many of you will recognize them as sort of calibration errors. So for example, take this, this illustration here where we have a gear and a point cloud overlapping. You want to ask yourself, is the object in the right place? Is it of the right scale and form? In this case, we can see that it's clearly too large. It's tilted. It's a little bit offset. And this is more common than you might think. So you might sit in your lab, get the system running, start picking a couple of things. It looks fine. But the real task is when you try to put this into the real world. So what might happen if your system lacks trueness? So the first, the most simple one is, for example, that you might miss picking the object entirely. So the robot approaches, but it never really hits the object. Next is that the gripper maybe gets a poor hold and tries to move it around. You lose it halfway there, or maybe you misplace it at your destination. A little bit more severe is that the robot might crash into the object and destroy it, or maybe a neighbor item. Or the robot might even collide and destroy itself. Maybe break the gripper or misalign some pieces so that you need some human intervention to come in and reset the system, maybe change out some parts, etc. And this sounds sort of simple enough, but as we've been working with quite a lot of companies over the years, we realize that the likelihood that this happens is a lot higher than you are comfortable with. It happens a lot more than anyone dare to sort of admit. Some of the sort of more skilled companies we talk to are typically operating in the range of, say, 2 to 5% of mispick rates. And if you try to put that into some context, 2 to 5%, that's maybe 50 mispicks a day. And 50 mispicks a day, what does that mean? Well, for example, your effective cycle time, if you're targeting a cycle time of 500 picks per hour, you can typically double your mispick rate. So say if you have a 5% mispick rate, that's 10% reduction in effective cycle time. So maybe instead of doing 500 picks per hour, you do 450 picks per hour. And another thing is that if you do this quite a lot and you start reaching those lower two brackets there, where you interact or collide with stuff, you might actually start damaging parts, and that's very costly. So what you need to ask yourself is kind of, is the 3D camera I chose accurate enough to get an acceptably low count of mispicks? Or if you flip it around and talk and ask it from my perspective, coming from someone who makes 3D cameras, given any random chosen pose within the region of interest, what is the expected error? And this is an overview of some data sheets that you will find from most of the, or many of the popular 3D cameras that you find out there. Ours is on the top, by the way. It's not the easiest one to read either. We also have our mistakes and flaws. But this, if you start this exploration, you will probably come back more confused than you started. So, for example, here there's accuracy, 300 micrometers. What does that mean? I have no idea. So, and ours is also not great, but I'll try to explain it to you a little bit, how we think about it. So here's a setup with our Zivid 2 camera over a robot. We have the focus point. And then basically, what we use is the calibrated frustum. So what that is really, what is the working volume that our camera is designed to work in? So it's typically operating from, say, a meter above the bin, and it covers maybe half a meter by half a meter by half a meter cubic region or something of that sort. And then what we do is we calibrate the camera in a certain way, and we want to understand how is the point cloud distorted and scaled and misplaced or whatever in that entire working volume. So what we do is that we basically slice the entire working volume into a lot of different slices. And we look at basically, 1,000, maybe 5,000 individual measuring points or something of that sort for every slice. And we compare it to a very known reference. And so we create, for example, here a contour map which says something about how the point cloud differs from a known reference object. And this is very hard to do properly, actually. You have to have very tight control of the reference object, the temperature that's happening, all the systems that are working at this to really get this right. So we divide this up, and we basically, for every camera that we test this way, there's approximately 20,000 unique XYZ coordinates that are correlated with its real point. And then we gather all this together, and we make some statistical analysis and say, for example, what is the median error, or what is the 70% chance of an error, or limit of an error, etc., etc. But we can't really stop there, because a 3D camera is a mechanical, physical device, and they have atoms. And atoms, they react to heat, for example. So what we do is that we repeat this measurement across different temperatures. So we change the temperature to maybe, say, 5 degrees centigrade, or 20 degrees centigrade, or 40 degrees centigrade, and we repeat the whole shebang. And we look in every point in that whole volume and see how does that change as the temperature changes. And then we do the same again when we exert other types of stress tests. For example, what happens if you shake the camera and repeat your measurement, or what happens if you hit it, repeat it, or what happens if you sort of try to cook it, or like stress test it from like an aging perspective. And we repeat all these measurements, and we collect everything into a huge, huge pile of data. And that gives us a model for how wrong our camera is for that one camera. And then we do this for a lot of cameras. Typically, when we make a new product, we can test maybe 50, 100 cameras this way, something like that. We try to get a pretty big statistical certainty. And then we bake all of that stuff into a massive data set, and we try to figure out what is the dependency to temperature, what is the dependency to shock, vibration, moving it on the robot, what about different spaces that you're looking at, regional, global, whatever. And then we create a data sheet. Sounds pretty boring, and it really is, but yeah, we feel we have to do it. So basically what happens is that then that out of all these measurements, the numbers that pop up in our data sheets, they include statistical errors from field of view and working distance, basically the volume we're looking at, operating temperature, handling, wear, tear, aging, and production and unit-to-unit variation. A lot of these tests that we do, we test on every single unit that is going out. And so, for example, here on the right side, you can see an example where we have mapped the different error contributions for a large set of cameras, and look at what is the, if you basically look at this every slice in this frustum, what is the 70% limit of error for that slice? And then we map that against distance, and you see, for example, calibration residuals, they contribute that much, temperature contributes that much, shipping and moving on the robot, etc., contribute this much. And we do this so that you can know when you make your applications what your error margins are. Because from those data sheets we saw before, how are you going to use those to assess what your error margins are in your applications? So basically, the dimension trueness error that we try to extract is the way you basically use this is that you assess the distance of what you're looking at, or the size of what you're looking at, and you simply multiply it. So for example, say that you have an object that is 1 meter away from the camera, and you have a 3D camera that has a 70 percentile trueness error of 0.1%. Well, that's 1 millimeter of error margin. Pretty straightforward. And then there's, of course, hand-eye calibrations and robot calibrations and all that other crap on top of it. But at least from the camera part, we can try to cover some of this. So this is actually not that difficult to assess your error margins. And the reason is simply that the reason why we go through all this is that we're making industrial products designed to be deployed reliably at big scale. This sounds quite simple and sort of obvious, but you have to remember that 3D camera systems in the industry is still sort of an emerging thing. There's not a lot of big players like there's no Toyotas in this industry that's been doing this and perfecting this for decades. We're still sort of ironing out all the different errors, and we have a fair share of our own. But we know that once you start deploying not 1, not 10, but 100,000, 10,000 of those systems in the real world, and you have a 2% picking error for every cell, well, that amounts to a lot of problems. So we are trying to take control of it and let you know what we can deliver, and basically so that you have transparency into how the camera works. And typically, the datasheet numbers that we show are covering sort of 95-ish% of all products. So you're most likely to have something that's within that range. And basically, we try to take care of that so you don't have to. So I kind of concludes my talk. I just wanted to scare you a little bit with something unknown error sources that are greatly underappreciated in this industry, and prepare you a little bit for all your deployments in the future. And as always, see more and do more. Thank you.
Thanks a lot. Guys, hello. Hi.
Anything? Questions?
We have a couple of minutes for questions. Do we have questions from the audience? Any questions? Yes.
Okay. Then, there is a question. Okay.
Yes, there is one.
Thank you. Thank you for the presentation. You were talking about false points. So that's a great issue with 3D cameras.
Yeah.
Do you have any metrics to assess the quantity of false points that your camera have on, for example, specific surfaces or shapes?
So internally we do have some, but I would say that it's when it comes to, for example, reflections and these kind of things, they are extremely sensitive to basically what you're looking at. So it's very, very hard to say find some universal or global thing for it. While calibration problems have sort of a limited set of dimensions where you can go in comparison to like how much crap can I throw into this thing and look at what happens. So no, we don't really have a very good metric for that today, and I think it is also related to the fact that a lot of different 3D cameras have different ways of dealing with it, and you have typically some filters that you can tweak and tune and sort of try to adjust. While, for example, the underlying calibration is sort of, that's what it comes with. So you don't really, it's very hard for you to control that in an effective manner. So short answer, no, we don't have a good metric for that today. And I think it's going to take some time until someone comes up with something that is simple and memorable enough to capture it as well, unfortunately. That's just my take on it.
Okay, thank you.
Thanks, Erwin, once again.